I recently came across a video about a hover bike on Colin's channel. As you can see in the video, it's a pretty cool project, and he was able to build it and have some initial test flights with it, although he didn't build a control system for it. So in this video, we're going to look at what a control system would look like for this hover bike. We'll start with a quick discussion on whether it's possible or not to control flight on a two-propeller craft. We'll then do a quick review of one of the helicopter technologies needed for a control system. And then we'll wrap it up and talk a little bit about how you can control movement in the different axes on this hover bike. Let's get to it. Looking over the comments of this video, I noticed a trend that people were suggesting that he needed to add 2 more propellers in order to achieve stable, controlled flight. As you can see in some of these that I selected, you see things like a forward and backward propeller, or in the next one, there's nothing to stabilize it, and the leaning to side, that's where you need 3 or 4 prop. And the next one, it says you need forward thrusters. And the one on the bottom left, it says all he needs is 2 more props. On the top right, you see since there's only 2 fixed props, a difference in engine power won't control yaw or roll. And they both seem to be the major difficulty to control. Another one, you need the thing on the back of a helicopter. Another one, it says, my suggestion about copter gyros is just to have pitch under control, which is all you can do with 2 props. And then of course on the bottom right, someone is suggesting adding tiny jet engines for steering and forward thrust. So the question is it possible to control something with only 2 vertical axes or vertical facing propellers? And the answer is yes. A resounding yes. In fact, it's already been done before. So let's talk about some of the helicopter tech that you would need, and then some of the propeller effects, and then go into how we would control movement in the different directions. Over the years, we've seen developments in propellers. Way back in the day, they used to be fixed pitch. So fixed pitch is just what it sounds like. The pitch doesn't ever change on it. Then came along adjustable pitch propellers, or sometimes called ground adjustable pitch. These propellers could only be changed while the airplane was on the ground. The mechanic would have to unbolt the propeller, adjust the pitch, and retighten it down. After that came along variable pitch. This was a propeller that you can change the pitch of the propeller while you were flying in the air. This also gave way to constant speed propellers, where you could run the propeller at the speed that was most efficient for your engine, and then change the pitch to either get more or less thrust out of it. However, helicopters took it one step further with swash plates. The idea behind a swash plate is it gives you what's called cyclic pitch control. The swash plate is essentially a bearing. On one side of the bearing, you have the fixed linkages that go into the helicopter. On the other side of the bearing that rotates with the blades, you have another set of linkages. And so what this allows you to do is to pull down on one of those non-rotating linkages to move the orientation of the swash plate by lowering one side and consequently raising the other side. And by tilting the swash plate, the linkages that rotate with the propellers actually will change the pitch of each blade depending on where it is in the rotation. So if that blade is near the high side of the swash plate, that link is going to push on the blade and create a higher pitch. If it's on the lower side of the swash plate, it's going to create a lower pitch on the propeller. To understand control of the craft, we need to understand the effect these propellers have. The first effect we're going to look at is reaction torque from the motor. We know from Newton's third law that if you push on something, it pushes back. Well, the motor is pushing on the propeller to turn it, and therefore the propeller is pushing on the motor in the opposite direction. This is the reason that traditional helicopters have a tail with a rotor on it, so that it can provide a counter torque to this reactionary torque Now with the hover bike, if we made one of the propellers spin in the opposite direction as the other, we call this counter-rotating propellers, then the reaction torque that's developed when the motor pushes on the propeller and the propeller reacts and pushes back on the motor is going to be canceled out by the other propeller's reactionary torque. And so with this two propeller system, we don't have to worry about the reaction torque from a motor causing a yaw. Another propeller effect is gyroscopic precession. There's actually some pretty cool physics going on behind this phenomena, but I'm going to simplify it and say that if you rotate about 2 axes, you have a third rotation and the third axis. For a traditional helicopter, the spinning propeller is rotation about the first axis. When you pitch up or pitch down, that would be rotation about the second axis. And it's going to cause the helicopter to want to rotate about the third axis, which in this case would be rolling left or right. The same thing happens if you try and roll left or right. The propeller spinning would be rotation about the first axis. Rolling left or right would be rotation about the second axis. And so it wants to induce a rotation about the third axis, which would be pitching up or down. Now here on the right, for a two propeller system, you don't have to worry about gyroscopic precession. That is because due to the counter-rotating propellers, if you pitch up or you pitch down, one propeller is going to want to roll left and the other one is going to want to roll right, and it's going to cancel each other out. Likewise, if you roll left or if you roll right, one of the propellers is going to want to pitch up and the other one's going to want to pitch down, and they cancel each other out. Another propeller effect is P factor, or propeller factor. This comes about when the rotation or thrust axis of the propeller is not aligned with the flight direction. And long story short, as the propeller rotates, there's going to be a difference in blade velocity, and the angle of attack that the blade sees is different whether it is ascending or whether it's descending. Essentially causes the propeller to produce more lift on one side than the other. It's kind of similar to what a swash plate does, but it's not due to any mechanical changing of the propeller. It's just due to the way the air is flowing around it and the blade is spinning through it. Now on our two propeller aircraft, we actually don't have to worry about this, because with counter-rotating propellers, one of the propellers is going to see more lift on one side and the other propeller is going to see more lift on the other side. And so this propeller factor cancels out when you use counter-rotating propellers, thereby simplifying the controls that we will need for our two propeller aircraft. All right, let's go ahead and talk about one more propeller effect, and that is the slipstream that is developed from a propeller. As you can see by this aircraft on the left, as the propeller spins, there is a wake or a slipstream, and it is both traveling backwards and rotating at the same time. It gets pretty complicated when you're looking at an aircraft, because depending on which way the propeller is spinning, the slipstream can be either wanting the left wing to go up and the right wing to go down, or the right wing to go up and the left wing to go down. And it also can affect your elevator and rudder. Now for our two propeller aircraft, and for instance the Chinook helicopter, it's a little bit simpler than that. What happens is that with these counter-rotating propellers, the side of the helicopter that the propellers sweep towards is going to have the slipstreams kind of hitting the side of that aircraft, and it's going to want to drift towards the other side. Now we will have to take this effect into account, but it's easy to manage. Usually we just design the craft to have a slight roll towards the side that the propellers are sweeping towards the body. So that way that very tiny amount of roll is actually canceling the drift developed by the slipstream. Let's go ahead and talk about how movement can be controlled in the 6 degrees of freedom. Let's start first with moving up and down. If you want to move up, you need to increase the lift of both propellers equally above the gravitational force on your aircraft. And if you want to go down, likewise, you would decrease the lift on your aircraft below gravitational force. Now you're going to do this equally on both blades, and you're going to do that by either increasing or decreasing their speed and or their pitch. Now let's talk about moving forwards and backwards, or rotating the aircraft's nose up or down. On a two propeller aircraft with the propellers arranged so that one is towards the nose and one is aft, This would be accomplished by increasing the lift on one propeller and decreasing the lift on the other. This is going to cause the aircraft to pitch either up or down depending on which one you chose to increase or decrease. Again, this can be accomplished by adjusting their speeds or the collective pitch on the propellers. And so what happens when you rotate about this axis is that the direction of the total lift is going to go from being vertical to being angled slightly forwards or slightly backwards. And using vector calculus, so we can split up that total lift vector into a component that is vertical, and this would be the component that's counteracting your gravity, and then a horizontal component. And that horizontal component is either going to be moving the aircraft forwards or moving the aircraft backwards. Now let's look at horizontal movement left or right, or inducing a roll in the aircraft. This is one of the reasons we need this swash plate on our two propeller aircraft. And what we're going to do with that swash plate is that we are going to raise the swash plate on one side for both propellers, and thereby also decreasing the swash plate on the other side for both propellers. Now it's important you do it on the same side because we're going to talk about a different direction control on the next slide where we're putting them on opposite sides. And so what this is going to do is something similar to before, where we're going to have more lift on one side than the other side, and that is going to cause our aircraft to rotate into a roll. And similarly, we'll have a total lift force that is angled slightly to the right or slightly to the left. And using vector calculus, this total lift force can be broken up into a lift component that's counteracting the gravity or weight of your aircraft, and another component that's contributing to horizontal movement either left or right. Let's talk about the last degree of freedom, and that is rotation about the vertical axis, also known as yaw. This would be the other reason that we need a swash plate for our two propeller aircraft. To induce a yaw, we're going to use the swash plate so it's opposite on the propellers. What this is going to do is that on one propeller, it will have more lift on one side of the aircraft, and on the other propeller, it's going to experience more lift on the opposite side of the aircraft. For this front propeller, the more lift is on the right side. This is going to want to cause the front propeller to roll to the left. However, the back propeller has more lift on the left side, and that's going to cause it to want to roll to the right. And so one propeller wants to roll one way, the other propeller wants to roll the other way. And so this rolling is canceled out. However, this difference in lift leaves a horizontal component with a moment arm about the center of gravity that's going to want to yaw the aircraft. Another part of a flight control system that we need to take into account would be the human control inputs to the system, whether that comes from a pilot actually riding on or in the aircraft, or whether that's coming from a remote pilot who's controlling it with a wireless transceiver. For a helicopter, you see they have pedals, they have a cyclic control or the stick, and the collective. There are several different ways to incorporate this. Obviously, if your aircraft was a UAV, you can have different joysticks doing different things. If you're riding it like Colin is in this video, I don't think it would be too hard to come up with your own inputs to the system. He could still use pedals in his current configuration. He has a bar that he holds on that could easily be allowed to move to be able to control the cyclic control. And you could easily have a thumb throttle, or more like a motorcycle, where you have to twist your wrist as a throttle control, or perhaps as a collective control. You could also simplify it a little bit, and since this is supposed to be a quote-unquote hover bike, maybe you simplify it where the control system worries about the collective or the throttle, and it just tries to maintain a certain height above the ground. You obviously would have to worry about some sort of cliff detection safety. You could even lose the pedals and incorporate it into the bar that he holds onto, where you can either push it forwards and backwards, left or right, or spin it. So there's several different ways to do the human inputs into this hover bike. And then of course you get all the fun with having to worry about command shaping and feel of the joystick and handling and flying qualities that come along with it. Let's go ahead and end it here. If there's another video floating around on the internet that you want me to review, just drop me a link in the comments below. And in the meantime, don't forget to like the video and subscribe to the channel. I'll see you in the next video.